All right, we're back, and in this video, we're going to be talking about something known as overflow. Not a ton of coding in this one, but there's a little bit. It's mostly just going to be me poking around in IntelliJ. Feel free to follow along with that whenever we get there. So in Java, and it consumes 4 bytes or 32 bits of memory. We talked about this in our binary video about the amount of data that an integer consumes. Okay, what do we mean by that? Well, whenever you declare an integer in Java, it's going to set aside 4 bytes. And effectively, your integer has to fit into that, right? 4 bytes being 32 bits because 1 byte is 8 bits. And we ask this question, what is the largest number that an int can store? Keep in mind that positive numbers, negative numbers, and 0 must be represented. So the quick way to actually figure this out is that we take our base of 2, right? We're talking about binary. And the number of bits that we have, in this case 32, right? We figure out what that is, subtract 1, and that is the largest number that we can store, right? That's like 4.2 billion, okay? How many different different combinations? It's this number plus 1, but the largest number that I can store is this, okay? That is assuming what we call an unsigned integer. That is, you do not care about positive and negative, but in Java we do care about positive and negative, so we're going to cut that in half, right? We're going to put half the numbers on the positive side and half on the negative side, which means the largest number we can represent is, in theory, this. Okay, we're going to end up dropping this fractional part because I can't have a fractional part when I'm talking about integers. It's going to be a whole number, and effectively we're going to fit 0 in on the positive side. So we end up with these numbers, right? This is the max value that I can represent with an integer. This is the smallest value I can represent. The 0 is effectively on the positive side, right? Which is why this number is 1 less than the min value here. Now, it seems like an arbitrary number, but it is directly related to the fact that we are setting aside 4 bytes or 32 bits of data in order to store our integer. Okay, so there's something interesting that happens. If you attempt to store a number larger than this into an integer, we're going to get a compile time error, right? If I try to create an integer with this number plus 1, right, 2.1 billion, blah, 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 648, it's just not going to fit. Why don't I actually show that now? We'll open up IntelliJ, create some new little project, and kind of poke around. Quickly, the people are waiting. I have to get me one of those $1,500 graphics cards, right? Just convince myself that that'll make all of this go faster. Promise you I'm not operating on a potato. All right, so I'm going to ultimately create a new project here by going to File, New Project. I really just want some space to kind of poke around in, play with some numbers. So if you're wanting to follow along, feel free to do so, but not super important. This is one that you could just kind of watch. I'm going to flip over to my principles folder. I'm going to create a folder called Overflow, and I'm going to make sure that we have that subfolder created. I'm going to create a new class called Overflow. Doesn't really matter too much. I'm going to go ahead and plug in a main method with PSVM. And I'm going to create an integer. I'm going to call it max, whatever. And we're going to try to save in the max value of an integer. Okay. I'm going to pull it from my slides. Right? I'm going to grab this. And you know from previous lectures, previous slides, that we can't have commas. So let me take those out. But I'm telling you, this is the max value of an integer. Notice that I'm saving this in, IntelliJ is not mad. We'll go ahead and print it off to make sure there's also no runtime errors. I'm going to right click in free space, tell it to run, and we should just get that number directly into our console. No errors. The important thing here is no errors. I was able to take this quite large number, store it into an integer, print it off, blah, 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 blah. All right, if I go one more, that's a compile time error. Right? I can't do this. I can't fit a number this large into my integer. And again, notice I'm not running the program just yet. It's already detected an error. This is a compile time error. It's able to catch this before I even try to run the program. Okay, that's what this slide is saying. Attempting to store a number that is larger than this into an int will result in a compile time error. And as you can imagine, if we were dealing with a negative number, right, this is the smallest value that I can put into my integer. And again, notice there's no issue. Maybe I should call this min instead, not to drive people crazy. Or why don't we just make a separate one? I'm going to grab this. We create our integer min, which is a negative value. I'm just going to comment this bad boy out. And then I'm trying to print off min. No compile time issues. If I tell it to run, we'll also see that we're getting no runtime issues. If I try to go one smaller, instantly compile time issue, and if we try to run it with a compile time issue, we're not even going to get anywhere. Integer is too large. Okay, that's what this slide is ultimately saying. But an interesting phenomenon happens whenever you increase an integer beyond the maximum value or decrease it below this value. Right, here's my smallest number, right? I think most people probably understand the max a little bit more, so let's bring that back in. So I have the maximum value, no compile time issues. No compile time issues. Okay, what I'm going to do is instead of just increasing it by 1, what if I add 1? You notice IntelliJ has highlighted this with yellow. It says numeric overflow in expression. I'm going to run this. There's no compile time issues. Nothing is read. And then we get, whoa, this number. Right? So what happened here? This is effectively the lowest value possible. I had the maximum value possible, and I tried to add 1 to that. And what I ultimately ended up with is the lowest value. If we were to try to add, say, 10, let's see what we get from this. I end up with this number. So what's happening here? This is overflow, and overflow occurs when the result of a calculation exceeds the range for that number type. As we're going to see in the future, this number range differs based on what we're dealing with, what data type we're dealing with. I'm talking about int versus double. And then there's other data types, right? We know there's 8 primitive data types. Byte, short, long is an important one. Okay, they each have a certain capacity which affects their range. We're looking at the range of an integer because it's the most important one to us. And overflow can occur whenever we try to exceed the range for that number type. The excess result beyond the range of the number type will wrap around and continue on the opposing end of that number type's range. So if I'm at the max value of my integer and I try to go over it, what's going to happen is that we wrap around to the negative side. Okay, that is overflow. Now, if we were at the negative side and we tried to go even further negative, we're going to go back around to the positive side. Let's demonstrate that. Right? I'm going to comment this bad boy out. We'll bring back in our minimum value. Right? I'm going to change this to min. No issues. No compile time issues. Right? If I try to do a 9 there, we got problems. But if I subtract 1 instead, what do you think is going to happen? I'm at the smallest value, and I go -1, and it wraps around to the largest value. This is overflow. Okay, and then there's some slides kind of demonstrating this. We actually take the largest value of an integer, and we tack on 10, and it's going to wrap around, give us this number. Over here we have the smallest number, we subtract 10, it's going to wrap around, give us this number. So that's where I'm going to leave you with this number file video where he talks about the end of time with Unix. Super interesting, lots of applications to Overflow. It is a big meme in the programming field because this is related to, again, binary. This isn't a Java issue. It exists in binary, which means all programming languages ultimately have this as a thing. And as it turns out, most statically typed programming languages, such as Java, C++, they use 32 bits for their integers. Okay, well, this video is going to talk about how we use values to basically figure out time. Effectively, we count from January 1st of 1970, like how many seconds have passed. Well, what happens when we hit the max value of an integer? It's going to go negative. We'll have negative time, right? It's going to roll back. The problem with Overflow is ultimately there's no warning, right? Notice in these cases, the only warning I have is IntelliJ, which that's just because IntelliJ is awesome. IntelliJ is giving me a warning that we're going to have that issue, but there's no compile time issue. There's no runtime issue. It's just the IntelliJ warning. So there's really no warning that overflow will happen. And it can be remedied kinda using the long data type, right? With long, it is twice the capacity of an integer. That means it is 64 bits as opposed to 32 bits, okay? With that, it still has the issues. Here is the max and min value of long. Overflow can still happen here, but this is quite a large number, 9.2 quintillion, I believe. And so it can help kind of slow down or remedy just a little bit some of these issues. In theory, we eventually get overflow, but quite rarely do we ever in computer science, in any type of application, come across a number that we need that's this large. Okay, so for the most part, long helps with that. Now keep in mind, it takes up, right? It takes up twice as much space as an integer. And we talked about why use an integer over a double. It's the same issue here. Why use an integer over a long? Well, when you get into big data where there's lots of numbers, for us, I'm working with literally one integer here. Space is not a huge deal. But when you get into big data, we're talking like number of credit card transactions a year. If you're storing those things as long, you got a bit of a problem. Kind of to put it in perspective, one of the most prevalent issues, or one of the most prevalent cases where there was integer overflow, is with YouTube. So this is the most prolific case that I can recall, but YouTube, the viewer count, was originally using an integer to store number of viewers. In YouTube's mind, they were using that 4.2 billion. They were using an unsigned integer, right? Because you don't need a negative view count on a YouTube video. And they thought that no video would ever get 4.2 billion views. That's crazy. And then Psy's Gangnam Style, you might recall the video, actually surpassed that. And it went basically negative. It went to 0. Maybe they were using assigned, because I remember the thing was it went negative. So in theory, they were thinking that no video would get 2.1 billion views, and Psy's Gangnam Style did, and the view count went negative. Okay, so that was a problem. So YouTube had to go in and change the way they were tracking view count. But here's the thing: every YouTube video has basically that bit of data attached to it. All right, so in a database, YouTube is having to not only store the video, which is a huge amount of data, but they're storing how many views does that video have for every video. Right? They want to use the smallest data possible. They want to use an integer, but if it doesn't work, they ultimately had to upgrade the system, and so now they actually use long. They use the long data type, and so in theory, no video should get 9.2 quintillion views. So in theory, this problem is solved, unless something gets 9.2 quintillion, and we're going to overflow and get a negative value. Okay, so that's essentially it for overflow. The only thing I can really talk about is why it effectively occurs. They talk about it a little bit in the video, but let me just quickly show you because I actually do have a pretty good explanation here. They use 4 bits in the video to demonstrate the idea, the number file video that I will link in the description below or on the as a suggested video. But with 4 bits, right, it looks like this, right? And we're going to count up. We go 0, 0, 0, 1. And we're going to just keep going. Sorry, trying to space this out. You'll see why in a moment. So the max number that I can store with 4 bits, it looks like this. Okay. Right, off the top of my head, what is this? This is 1s, 2s, 4s, 8s. This is like 12 or 13 or something. Not important. Oh, it's 15. Duh. It's 15. Okay. The next number in our binary series would look like this. But let's say we're working with a system where we can only have 4 bits. What's going to happen is, once we go from this number, right, let's say that we're adding 1, we would in theory get this number, except I can only have 4 bits. So we're going to just throw away that bit. What has happened here? I've gone from the maximum value possible and wrapped around to the lowest value possible. That's what's happening with overflow. That little extra bit right here, it's just getting discarded. There's nowhere to put it, right, in this 4-bit system, okay? Now just this exact same scenario, scale it up to 32 bits, or in the case of long, 64 bits, right? And that's what's happening here. That's what's causing it to overflow. Now this number is 0 because this is basically unsigned. But if you take that scale, this number range, and you just shift it so that you're including negative numbers as well, this is effectively the minimum value, and this is effectively the maximum value. So we're wrapping around from the maximum value back to the minimum, and we can go vice versa. So that's going to be it for overflow. Ultimately, you know, as you can imagine, 9.2 quintillion, it is possible. It's possible to go larger than this. That's where you're going to need, in the case of Java, some objects, something known as big integer or big decimal. Don't worry about it too much, but there is possibilities. I'll see you in the next one.